When it comes to developing new ideas, there have been many prominent achievements that evolved from simple beginnings. The Ford Casting Process Development Center is a key example of an innovative endeavor that has continuously risen to meet new and demanding challenges. Located next to the Windsor Aluminum Plant near Windsor, Ontario, the facility, originally known as Cast Aluminum Research and Development, was built in 1988 to support a casting development program. The program was based on Ford's initiative to turn low-volume Cosworth racing manufacturing techniques into processes that could be used for high-volume engine production. Initially, Ford engineers staffed the operation. Later, that number grew to include a supplemental workforce of co-op students from local universities and colleges. Together, the Casting Process Development Center team developed a feasible process for applying this racing technology to high-volume production castings. Based on the success of the effort, Ford built the Windsor Aluminum Plant, a full production manufacturing facility. The company also upgraded the Casting Process Development Center for process and product prototype development. Since then, the Casting Process Development Center, or CPDC, has become one of the most flexible and innovative facilities of its kind. The facility has been an integral part of the development of aluminum cylinder blocks, heads, and other automotive components. From a cast-only facility, CPDC became a fully capable casting operation with the ability to perform quick processing in simulated make-like production and timing. The core area consists of make-like production machines and related lab testing facilities. CPDC produces cores weighing anywhere from several ounces to hundreds of pounds to more than 1,000 pounds. Small job shop core machines and quick-build core boxes are utilized for rapid prototyping with the emphasis on fast build and low cost. In the past, CPDC poured some of its castings manually. Today, through continuous improvement efforts, we've advanced to a semi-automated GPS pouring system for improved product quality and reduced cycle time. The new system also enables us to address manpower and health and safety issues. Although we've embraced new technology, CPDC continues to improve the precision electromagnetic pouring process we were originally chartered to develop. This offers the advantages of improved cycle time and maximized mold yield. A thermal sand removal process is used to reclaim the sand. This provides a much cleaner and more environmentally friendly means of removing the casting while minimizing the risk of damage to the part. It also allows us to reclaim more than 98% of the casting sand for reuse. Once the casting has cooled, it is degated, deflashed, shot blasted, and in some programs, partially machined. So that it meets or exceeds all customer expectations, the casting undergoes functional testing for process confirmation. At CPDC, these capabilities include Xyglow, X-ray, Layout CMM, Brinell hardness testing, air underwater leak testing, ultrasonic crack detection, borescope internal passage inspection, sand lab testing, and metallurgical lab testing, which includes both image analysis and mechanical property testing. When CPDC began as Cast Aluminum Research Development, it was designed to simulate make-like production processes. The success of this operation resulted in process improvements at the Windsor Aluminum Plant. CPDC developed the cast-in liner process for Ford Motor Company, which has been used in the production of engines since 1991. CPDC developed the talc core coating process, which significantly enhances casting cleanability. This process is being developed to include core definning. CPDC developed the thermal sand removal process, which uses non-destructive thermal energy to remove the sand from a casting. This process also thermally treats the casting while reclaiming the sand for reuse. For thermal stability, final heat treating of the casting can be performed in the aging oven. And through development of a fluidized sand bed, CPDC is evaluating the feasibility of an improved process for sand breakdown, as well as solution treatment and quenching of castings. Another operation unique to CPDC is thermal fatigue testing, which allows us to test components individually. This provides a rapid, single-step method of evaluating cylinder head process and design parameters. In conjunction with thermal fatigue testing, we're evaluating a number of non-destructive crack detection techniques, including infrared and ultrasonic methods. And we're working to develop better products and better casting methods for Ford facilities around the world. As part of our vision, we're working to develop innovative and robust processes that produce best-in-class products. We're working on automotive prototypes and processes that support the needs of customers from around the globe. We are working toward the continuous improvement not only of products and processes, but of people and the way we get things done. CPDC is a customer-driven facility, and through advanced quality planning, we're working to help Ford build and assemble the best possible products well into the next century. Some of our forward-looking projects include components for a hybrid electric vehicle, I-4 and I-5 blocks and heads, as well as heads for the 2.49 DAMB, 5.4-liter 3-valve, and 1.2 and 2.0-liter engines. Transmission cases with integral valve bodies, alternate mold materials, and robotics development. Beyond our role as a development facility, CPDC is also committed to being a good corporate citizen. We promote and maintain an environmentally friendly workplace, and we actively support the community through efforts which include 100% participation in the United Way campaign and the funding of related university research programs. CPDC. While our initial purpose may have been limited, through time and experience, we've learned that our capabilities are boundless and in harmony with the company's initiative for leadership.
At the Lampe Core machines, reclaimed zircon sand is mixed with a small amount of liquid resin. The sand and resin mixture is blown into steel molds with compressed air. A catalyst is used to harden the resin sand mixture into the shape of the mold, forming each of the 20 cores required to make up a package. cast iron bore liners are placed in the proper core box and are blown into the barrel slab core. Robots working in conjunction with a Bleichert pallet conveyor remove the cores from the core boxes and assemble them into casting packages. The packages are delivered to the rollover by a Bleichert conveyor.
The sand package is removed from the Bleichert conveyor by a robot and loaded into an induction heating unit. This unit heats the cast iron cylinder bore liners in position through the sand package. The liners are heated to allow complete bonding as the liquid aluminum is poured around them when the package is filled. The sand package is removed from the heater and loaded into the rollover by a robot. The rollover clamps the sand package and holds it during the pouring operation. Then it rolls the package and casting over 180 degrees to take advantage of the best pouring orientation. Liquid aluminum is pumped into the sand packages at the rollover machine by a Cosworth pump, which works by creating a magnetic field in the aluminum and an opposing field in the pump. This causes the aluminum to flow out of the pump.
After the packages have been filled with liquid aluminum, they are transferred by robot to the thermal sand removal oven. In the oven, the resin is burned out of the sand at 500 degrees centigrade, allowing the clean sand to leave the oven and travel to the sand system to be cooled and screened. It is then sent back to the core machines for reuse. In the oven, the castings are cleaned as the sand falls away and heat treated at the end of the oven in an integral air quench. The castings proceed to a saw where the gating system and risers are removed. The castings are shot blasted to remove the last of the sand.